In Chapter 5, we're going to learn more about exponents and see how to use them in something called polynomials. So 5.1, we want to review a little bit what we know about exponents and then start to look at some new rules that will help us to simplify expressions involving exponents. Take a minute to pause the video and try number 1 through 5 here. A little bit of a warm-up, a little bit of what we talked about back in Chapter 1 when we first defined exponents. So for number 1, 31 squared, you might remember that you have a squaring button on your calculator. Oftentimes it's x squared. So I'm going to type in 31 and then hit the x squared button on my calculator. You might get the answer straight away, or you might need to press enter or equals to have it finished, carried out. Looks like 31 squared is 961. Just a little bit of lingo. You might recall that the 31 is called the base, and the 2 there is the exponent or the power. So we could read this 31 to the second power or 31 squared. 3 to the fourth power. We're going to need a different button because it has a different exponent. So this time I'm going to start by typing in the 3. And then some calculators, you might recall, have this caret symbol. Others will have something more like x to the y or y to the x that you'll type in after the 3 and before the 4. And then enter or equals to get your answer. So 3 raised to the fourth power looks like it's 81. The next one has some parentheses around it, and those parentheses might prove to be significant. Notice number 3 and number 4 are very similar. Only difference is the parentheses. In number 3, the base is the -2, since it's inside the parentheses, and the exponent outside the parentheses is the 3. So we want to think about repeating that -2 3 times and multiplying them all together. You might have some parentheses on your calculator, so you could just type it in like it looks, -2 to the third power, parentheses and all. Or you can multiply -2 times itself 3 times. In either case, we should get an answer of -8. Number 4, it's going to be just a little bit different because this time that exponent of 3 is only attached to the 2. So in this case, the base is just the 2, not the negative. The exponent is still the 3. In other words, it's kind of like there's an invisible -1 there out in front of the 2 to the third power. And what that means is we actually have more than one operation. We have an exponent and a multiplication. We know from PEMDAS that the exponent comes before the multiplying. So the 2 is going to be cubed, which would make 8. And then we'll multiply that by -1 to get a final answer of -8. Turns out to be the same in this case, but if the exponent had been different, maybe an even number, the answers would not be exactly the same. So it does kind of matter. Number 5 also involves multiplying and exponents. So we want to make sure to take care of the exponent first. 6 squared is 36, and then the multiplying. 5 times 36. Looks like our final answer is 180. So take another minute to push pause perhaps and see if you can work backwards. Notice now we have the answer and we'd like to go back and write it as an exponential expression. So in other words, what number raised to what power would make each of these results? Try it out and see what you get. So 27 comes from 3 cubed. 36 comes from 6 squared. If I want that result 36 to come out negative, then that 6 squared should have a negative in front of it, kind of like we saw here in number 4. In other words, it's like an invisible -1 multiplied by that 6 squared. And lastly, for number 4, there's a couple of possible answers. Maybe you were thinking about 1 over 9 being squared, or since 9 also is a perfect square, we could even break it down to 1/3 raised to the 4th power. So that's a little bit of warm-up. The first new thing we want to see, the first rule we're going to come across is called the product rule. And you might recall that the word product means we're multiplying. So what we have here is an exponential expression like 3 to the 4th multiplied by another exponential expression. Because they're multiplied, that's why we're calling it the product rule. It's not a coincidence, by the way, that these bases are the same. What we're wanting to look at here is what happens when we multiply exponential expressions that have the same base, or in other words, they have like bases. So let's think a little bit about what this means. We know 3 to the 4th power is 4 3's multiplied together. And then we want to multiply that by 3 to the 2nd power, which means 2 3's multiplied together. So here's my 3 to the 4th. Here's my 3 squared, both all being multiplied together. So in the end, we just end up with a whole bunch of 3's being multiplied together. So it looks like the base is still 3. Let's see how many 3's there are. We had 1, 2, 3, 4 here, and then 2 more makes 6. So an easy way to simplify 3 to the 4th times 3 squared is to rewrite it as 3 to the 6th power. Notice that the base 3 stayed the same, and the 6 comes from adding the exponents. Because we're combining these 4 and these 2, we get a total of 6. As a rule, as a formula, you might see it written something like this: a to the n times a to the m. And if we notice what we did up here, the a part is going to stay the same, and the exponents are going to be added together, so the n number plus the m number. In other words, what we want to do is we want to keep that base a, and we want to add those exponents, n and m. Push pause for a sec and see if you could apply that rule to the examples down below. So with the y's, if we keep the base y and add the exponents 6 and 8, we get y to the 14th. With the next one, if we keep the base 5 and add the exponents, we get 5 to the 10th. And lastly, with the 8's, if we keep the base and add the exponents, we get 8 to the 13th. So that's what we mean by the product rule. Next up, we want to look at something kind of similar. This one is called the quotient rule. Quotient, remember, is a fancy word for dividing. So this time there's division. Dividing in between these exponential expressions. Again, it's no coincidence that these have the same base. We've got 3 raised to the 4th power divided by 3 raised to the 2nd power. So let's see what that means. We know 3 to the 4th means 4 3's being multiplied together. And down below, 3 squared means 2 3's being multiplied together. Since multiplying and dividing are opposites, we're just going to have some 3's cancel out. And let's see what's left. We still have a base of 3, but now there's only 2 of them. So a great way to simplify 3 to the 4th over 3 squared is to write it as 3 squared. Let's think about where that square there came from. There were 4 here, and then we canceled or took away 2 of them. Comes from taking away or subtracting. So that 2 is really a result of 4 minus 2. So when we're dividing like bases, we're again going to keep the base. Notice that there's 3's here and still a 3 there, so keep the base the same. And the exponents get subtracted. See if you could write the other half of the rule or formula for the quotient rule? Keep the base, subtract the exponents. So that would equal a to the n minus m. Try it out with the 3 examples down below. See what you get when you apply the quotient rule. Like, keep the base y, subtract the exponents, 6 minus 8 makes -2. Keep the base 5, subtract the exponents, 7 minus 3 makes 4. And keep the base 8, subtract the exponents, makes 8 to the 5th. That negative exponent's going to look a little strange for now. By the time we're done with chapter 5, we'll know what that means.